With the idea of controllability and observability um, now understood by us, we are in a position to talk about something called the canonical form. Okay, and minimal realizations, non-minimal realizations, these things. So if you remember at the very start of our course, we stumbled upon stumbled upon a realization, or stumbled upon something which I mentioned that there can be non-minimal representations, there can be non-minimal realizations. So there is an idea of minimal and non-minimal realizations which is linked to the actually controllability and observability. So we had to wait so far in order to come to the concept of minimal and non-minimal realizations. So let us now look into what these are. The canonical forms. So those realizations that are completely, so when I am using controllable and observable, you must understand I am implying complete controllability and observability. So realizations that are controllable and observable are called canonical realizations or canonical forms. So those forms which are completely controllable and observable are called canonical realizations or canonical forms. Forms means these representations. Okay, so for a particular system, you want to know that for a particular system you can derive some representation, your friend can derive some other representation. Now it is not for sure that both the representations will be controllable or observable. By some approximation, by some assumption, you might have derived the representation, your friend might have used some other assumptions and considerations and come to another representation. So one could be controllable, one may not be controllable. One could be observable, another may not be observable. So we are talking about those realizations which are both controllable and observable. When we have both controllability and observability, then we say that this is a canonical realization or a canonical form. Such realizations are also minimal realizations. That means they are constructed with the minimum number of state variables possible. They are constructed with the minimum number of state variables possible. How can they be constructed from a transfer function? If you construct there are formulas for ready construction of a state space representation from a transfer function. But if you are using a transfer function which is further reducible, means that there could be pole zero cancellation and you have not done the pole zero cancellation, then you would come to non-minimal realizations. And therefore, the minimal realization is the realization obtained from irreducible transfer functions. So where there are no pole zero cancellation possible. If you make a representation from a irreducible transfer function, then you would come to a minimal realization. Now just looking at a transfer function, if I give you in a numerator polynomial by denominator polynomial form, you would not know whether there could be pole zero cancellation. So if you straight away make a realization out of that transfer function, there is every chance that you would land into a realization which is either uncontrollable or unobservable or both. Also there is fair chance that you will come to a canonical realization. That is also true. But the point here that I'm trying to make is that if we want to come to minimal realizations, or if we want to get canonical forms, then we have to assure that the transfer functions we have used are irreducible. They cannot be further reduced. Now, all the story about similarity transformations and all, so they are valid. So I should say, like, they are also valid for non-minimal representations, but here what I'm trying to stress is that if you have two minimal representations, one is suppose R1 and another is R2, then there is a unique similarity transformation P between them. And if you come to R2 with P, then with P inverse you would come back to R1. However, if the realizations are non-minimal, then this phenomenon is not assured. That means the uniqueness of the similarity transformation, as well as if you will be able to come back to the original realization using just the inversion of the transfer function of the transformation, that is not assured. So this assurance is given only in case of minimal representations. So only in case of canonical forms, only in case of forms where you have controllability and observability satisfied, you would be able to go from one form to another using similarity transformations and again come back by using the reverse transformation, the inverse transformation. Please bear this in mind. Hence, when we are working with state space realizations, we would basically try to get the canonical realizations. Okay. So here is a fact that if a transfer function has one canonical realization, then all other realizations, so if a transfer function has one canonical realization of the order n being the order of the characteristic polynomial, then all other n order realizations will also be canonical. This comes from the fact that we can have similarity transformations between these canonical representations. So if you are certain that you have got a canonical representation, then using the transfer function, if I get any other nth order realization, then all those will also be canonical. And there is a proof around this. So suppose we have a realization ABC, then this C, there is a controllability matrix and observability matrix. So this, when multiplied together, gives rise to this particular matrix where each of these elements is basically called a Markov parameter, C a to the power of kb, where k can be any integer. This is a Markov parameter, and this matrix is called the Hankel matrix. So just a name, matrix containing Markov parameters as its elements. Now if I show that for two realizations the Markov parameters remain same, then that would mean that both would be canonical. So that is what we are going to show. Suppose there are two realizations A1 B1 C1 and A2 B2 C2 linked by similarity transformation. So there must be a similarity transformation linking between these two forms. Then this is the relationship, and hence C2 A2 K B2, you can write it as C2 can be written as C1P, B2 can be written as P inverse B1, and this A2 can be written as P inverse A1P, and this is multiplied K times, right? So what would happen there is a P inverse AP, then another P inverse AP. So this P and P inverse will cancel each other. So ultimately you will have a P inverse A1 to the power of KP within this bracket, and this last P is going to cancel with this P inverse, this first P inverse is going to cancel with this P. So ultimately you will get this. So this automatically shows that the Markov parameters remain unchanged in a similarity transformation. So the Hankel matrix would be same for any realization. This means that C1O1 will be equals to C2O2. So if your A1, B1, C1 is canonical, that means your C1 and O1 will be of full rank. If your LHS is full rank, your RHS must also be full rank, and for that to satisfy both the matrices C2 and O2 must also be full rank. So this implies that any pair of realization which can be connected through a similarity transformation will be canonical if one of it is canonical. Another fact about canonical forms: any two realizations are connected by a unique similarity transformation. So this connection with P, so this statement says that this P is unique. This is very simple to prove. Suppose we have two similarity transformations P and Q linking same two canonical realization. So that means to go from A1 to B, this system A1, B1, C1 to A2, B to C2, you can either use P or you can use Q. That is my assumption right now. Then what would happen with the relationship between the controllability matrices between C1 and C2? I know that PC2 would be equals to C1 as well as QC2 would be equals to C1. Remember that P is this C bar inverse, that thing we learned from the last lecture. That is what we are using here. So if this is true, then if you subtract, then P minus Q C2 will be equals to 0, but C2 is non-singular. C2 being non-singular, your P minus Q must be equals to 0 for this to be satisfied, and that means P must be equal to Q, which means the similarity transformation is unique. These two forms are very useful, and we would utilize this in the next lectures. These two forms are very useful. One is the controllable canonical form, another is the observable canonical form. In the controllable canonical form, the uniqueness of this is that, or the property of controllable canonical form is that the controllability matrix is identity. If the controllability matrix of the controllable canonical form is identity, then the transfer function going from that brings any state space realization to the controllable canonical form, this transformation is simply the controllability matrix of the parent realization. So from some realization you want to come to controllable canonical form. This realization is having controllability matrix C. So the transformation will be simply this C, because C bar is I. So P is basically C bar inverse, C bar is I. So I inverse is I. What is the controllable canonical form? The controllable canonical form looks like this. The ACC is in this manner. So these are the coefficients of the transfer function. If you remember, these are coefficients of the transfer function. Denominator polynomial, a characteristic polynomial. This is a matrix where you have the lower diagonal as 1, other elements are all 0. B is simply 1 0 0 0 0. Only the first one is 1, others are 0. Note the transpose. Observable canonical form, here the observability matrix is identity. That means the transformation to bring the system to the observable canonical form is simply O inverse, where O is the observability matrix of the parent realization. And the observable canonical form looks like this. This, if you remember, it's like the first companion form. C is here 1 0 0 0. Now, what about the non-minimal forms? We are talking about these canonical forms, which are the minimal forms. So there are this situation where we could get non-minimal forms. So that means there are certain modes which are not controllable or observable. So the realization may lose either controllability or observability or both if it is derived from a reducible transfer function, or in some way you are deriving from looking at the system and trying to understand the system dynamics. But while doing that, we have assumed some additional variables, additional state variables which are not required, maybe dependent on some other variables. You are not been able to understand that, and you have taken those state variables, you have derived the state space realization. In that case also you would get a non-minimal realization. What you would observe? You would observe that rank of the C matrix, controllability matrix, is less than n. This will imply loss of controllability. Rank of observability matrix less than n, it will imply loss of observability. This is very straightforward. You can do the column operation on the controllability and observability matrix to determine the rank. So you had simply determined that it is not controllable, it is not observable. But the question remains that which modes are not controllable, which modes are not observable. Modes, those modes of motion, right? You remember about the eigenvalues and eigenvectors? That is what we are trying to talk about. We are trying to catch those eigenvalues, catch those modes which are uncontrollable and which are unobservable. Are we able to do that? So that is the question. Yes, we can do that. There are some other ways also, but here I will give a very simple way. There is another way which requires some mathematics. I will not go into that mathematics for the scope of this course. If you take optional advanced control, linear control in your elective course, then there perhaps that can be covered, that will be covered. Here very simply you can identify the modes which are lost by taking the relation to the Jordan form. You can always do the Jordan form, whether a system is canonical or whether a relation is canonical or not. You can always do the Jordan form transformation. Bring the system to the Jordan form and note the B and C matrices. Note the B and C matrices. If there is a zero entry in place of an usually non-zero entry, then that mode is lost. This means I want to highlight this, that suppose in the diagonal form, let us talk about the diagonal form. So here is the lambda 1, lambda 2, lambda n, and all others are 0. So this is the x dot equals to this plus this into x plus b into u, and you know that in the diagonal form all these b's are 1 or some r1 r2 something. These are finite. Okay, This means that the control is able to affect all the modes, all the state variables, all the modes. The control is able to affect. If one of these becomes 0, if one of these becomes 0, suppose this is 0, then what does this mean? This means there is no way that I will be able to affect the state x2 or the mode lambda 2. There is no way I will be able to affect this mode. So the entire dynamics x2 dot equals to lambda 2 x2 will become independent of the control input. So I will not be able to affect this mode. Hence the controllability is lost on this mode. Similarly, if you have your C matrix, normally what is your C matrix? C matrix is also all finite elements. So for this relation, this would be R1, R2. These are the residues, right, of the partial fractions x. So y equals to this. If one of these becomes 0, suppose your some R3, this one becomes 0, that means the output is never affected by the x3 input, x3 state. The output is never affected by the x3 state. So the x3 state cannot be observed by the output. The information of x3 is not there in the output. So there is no way you would be able to observe x3 with the help of the output. So the observability is lost in this particular mode. What is this mode? This is the mode of lambda 3. The third mode, right? Lambda 3. So this one loses controllability, this one loses observability. So by simply doing a diagonalization or a Jordan form, you would be able to evaluate which of this will lose, which mode will lose controllability and which mode will lose observability. Doing the diagonalization Jordan form is very you know it is quite simple now. You have to start with knowing the eigenvalues, get the eigenvectors. So you, after knowing the eigenvectors, you get the modal matrix, and with the help of this you will be able to diagonalize. So you would be, when you get the modal matrix, and if your ABC is the original, this is the original representation, then what you are trying to see is M inverse B and CM. These matrices you are trying to see. So this is the M inverse B matrix, this is the CM matrix, and from there you would be able to determine which of the modes are lost. So you would not further do any investigation in this particular scope of the subject, whereas some things could be done. Actually there are maybe I will share a document which is a bit simpler to understand, but this does not form part of the course, but for those who are interested can go through that document and try to understand how we actually, from any realization ABC, we can, if it is a non-minimal, we can actually separate out the minimal or the basically the controllable and observable forms, observable part, and the uncontrollable and unobservable parts. This separation is possible. Okay, but we are not covering this in this course. With the Jordan form, we are only identifying, we are able to identify those modes. For the purpose of this course, the identification of these modes are only required, only important. And based upon this identification, we can now propose some additional concept about the about the system. Some additional idea about the system we can obtain, which is known as the stabilizability and detectability. So now we have identified the uncontrollable and unobservable modes. If the uncontrollable modes are stable, then the system is stabilizable. Why? Because the controllable modes I am always able to stabilize, because I will be able to control them. So if required, I will be able to, controllable means I will be able to bring them to 0, so it is stabilizable. If the uncontrollable modes were not stable, then I could not affirm this, because on the uncontrollable modes I don't have any control, right? So if they were unstable, then even by making all the other controllable modes stable, my system will ultimately become unstable. So for stabilizability, my uncontrollable modes must be stable on their own. So suppose you figure out that you have uncontrollable modes, but those uncontrollable modes are basically eigenvalues which are in the left half of the complex plane, which are negative eigenvalues with negative real parts, then you are fine. Then you can stabilize the system at least. You may not be able to control the entire system, but you will be able to stabilize the system. So at least for reaching 0, it is possible. For reaching anywhere else in the state space, we don't know. It is not controllable, right? But you will be able to reach 0. It is stabilizable. Same thing for observability. If the unobservable modes are stable, that means they will die down in some time. And after that, the system will be detectable. That means you will be able to detect the remaining of the states using the output information, because those states which we are not able to observe have already died down to 0. The remaining states you would be able to observe, and this is known as detectability. A final concept with which we will end this discourse on controllability and observability and these canonical forms, all related concepts, is called output controllability. Now always, state controllability does not infer output controllability. We have so far tried to understand whether the input, with the help of the input, we are able to drive the system to any state space, any point in the state space, or to bring it to any particular point in the state space. So the state controllability we have seen so far, and by controllability, if I just say the term controllability, you would mean state controllability. But this does not confer, or this does not infer output controllability. State controllability is neither necessary nor sufficient to establish output control. What is output controllability? Same way as we define state controllability, that is, we have a input, we have a initial output y0, and we want to go to a final output y1, whether the control input is able to take me to that particular output. So when I am talking about output controllability, this final one is basically 0, we can assume. So from any such input set, so initial condition set, we will be able to reach the final output, which is 0. Not going into the derivation of the condition of output controllability, just stating the condition, we need this matrix to be of rank P, where P is the number of outputs in the realization. What are these? These are the Markov parameters up to n minus 1, up to the nth Markov parameter. This is basically the nth Markov parameter. This D is also clubbed in. Normally the D would be 0. Normally the D would be 0. And we want the rank to be P, not N. Okay. So this matrix is, how many columns are there? So you see, I've also noted this. So if X is Rn, U is Rm, then this matrix is basically P cross n plus 1 m. N plus 1 into m number of columns are there. P number of rows are there. We simply need the rank to be P. That means there is a row rank must be full. For having row rank full or whatever, you can do the column operation always. The number of columns which would be independent will be P. Then you would have output controllability. Note that D not equals to 0 will always imply output controllability, because the output is directly connected to the input. So you can always give, you can always go to any output possible by giving the similar input, similar natured input. So that is all that I wanted to cover in this particular lecture, and thanks for your attention.